I'm going to spend a little time talking about the normal force because I found that this is one of the harder forces for beginning students to understand, and I can understand why. So I'm going to do the best I can to try and kind of elaborate this on this a little bit more than your book does and that most books do, in hopes that you can understand what the normal force is. Because most of the time when I see students having trouble writing down free body diagrams and solving more complicated physics problems, it's because of some misunderstanding with their concept of the normal force and what it is. Okay, so first of all, let's see what the normal force is. So let's say we have the floor and we have a box that's just sitting on the floor. Okay, well, we know that there's going to be a gravitational force acting on it. But we also know that the net force on the object is the sum of all the forces, right? And that's equal to the mass times the acceleration of the object. So if the only force acting on this object was equal to the gravitational force, then this is saying that we should have some acceleration greater than zero. And not only that, but that acceleration should be downward. But of course, if we see a block that's just sitting on the road, it's not accelerating, it's not moving anywhere. So there must be some other force that's missing, right? So I want you to take a second and think about, what must be happening in order for the object to not fall. So pause the video, think about it for a second, and then play again. Okay, so obviously there's a force that we're getting upwards, and it's coming from the floor. And this is what we call the normal force. So that for a block just sitting on the ground, we say, well, since we know that the net force is equal to the sum of the forces, so the normal force, and I'm going to define the positive y direction to be up. So it's going to be the normal force in the y direction plus the gravitational force, which says we have normal force plus minus the gravitational force. Oops. I'm going to enter that in the x direction. In other words, for the sum of the forces to be zero, which is what we require for the object to not be moving, then that's telling us that the normal force minus the gravitational force is zero, or in other words, the magnitude of the normal force is the same as the magnitude of the gravitational force. But in terms of vectors, of course, the normal force in this case is minus the gravitational force. Okay, but the important concept that I want to get across is this is not always true. Okay, because remember, the normal force's job is just to, this is describing the force from some kind of surface, a contact surface, against the other object, pushing back on the object. So for example, if I have something like a wedge, where now we have a mass that's sitting on top of it, well, gravity is still acting straight down. But the normal force, the reason we call it a normal force is, normal is another word for perpendicular. So you can think of this as a perpendicular force. So it's going to be acting on the object perpendicular to the surface. So it's going to form a 90-degree angle with the surface. Okay? So you remember from the last book that sometimes for problems like this, it's going to be easier to redraw it. So now we're going to call this this direction down the slope our positive x direction. We're going to call up the positive y direction. And so now we see that gravity is actually going to be at an angle here. but we see that the normal force is going to be pointed directly upward. And if this is some angle theta, then this angle, so the angle that gravity makes with the perpendicular here is also theta. So what this means is, if we look at the normal force now, again, from the way that we did it before, we see that this means that we don't want the object to fall through the ground, and so it's going to be opposing the downward force. So we see that our net force in this case is equal to the normal force in the y direction plus in the x direction the force of gravity sine of theta, and then minus the force of gravity cosine of theta. Okay, and the reason for this again is because we know that we have is that if this is the force of gravity, then its y component is pointing down, its x component is pointing to the right. Okay, so we know that the object, in this case the block, isn't falling, it's not falling in this direction, it's not going through the ramp. So we know that the y component, using this basis for x and y, has to be 0. So in other words, this tells us that the normal force minus the force of gravity cosine theta is equal to 0. So the normal force is the force of gravity cosine theta. Okay? So in other words, our net force is equal to 0 plus f of g sine theta, and then in the y components, these two are equal, so 0. So it's saying that we have a net force. So our net force is actually, pointing along, is equal to our mass times acceleration, and so it's saying that we're accelerating down the ramp, which is what we would expect. But there's one other quick case of the normal force that I want to mention before we finish the video, and that's the case where we have something like a wall, and we have an object against the wall, and then let's say we're holding it with our finger. Right? So if we're pushing up against this, then we're pushing with some force F. Okay? So I want you to pause the video for a second and think about where the normal force is. Okay, so a common mistake that I see is people trying to say that the normal force would be acting here, but that's incorrect. The normal force is actually, it has to be perpendicular to the surface, which is between the block and the wall. So we would have a normal force here. Now we can also call this a normal force too. This is a normal force, from our hand, and there's a normal force from the wall. And of course, if the block isn't moving left or right, this is saying that the force from our hand is equal in magnitude to the force from the wall. Or in terms of vectors, of course, they're equal but opposite. And so then so the net force, then we also have gravity, and we have other forces on it there. So that's the basic idea behind the normal force. So again, this is kind of an important force. It's one that's often overlooked, and one that especially in cases like the one that we see here, we see that the normal force really is perpendicular to the surface, not necessarily straight up. And I think that's the most common mistake that I see people making, when they're first learning physics. So, do your best to kind of fight that urge, and remember, that it's normal, it's perpendicular to the surface.